Given an integer array and a positive integer k, pick any subsequence and sum its elements. The empty subsequence counts as 0. The k-sum is the kth largest such sum, counting duplicates separately. Return that k-sum value. Example 1, nums 2 4 negative 2, k equals 5. List every subsequent sum, largest first. The top sum is 6, from 2 and 4 together. Next come 2 4s. Then 2 2s, the fifth largest is 2. The output is 2. Example 2, 6 numbers, k equals 16. We keep taking the next largest subsequent sum until we reach the 16th. That sum is 10. If we want to find the kth largest subsequent sum, our first instinct might be to generate every single subsequence, sum them up, and sort them. But with an array size up to 100,000, a 2 to the n brute force explosion will instantly crash our system. We need a way to generate only the top k largest sums without looking at the rest. Let's start simple. What is the single absolute largest subsequent sum we could possibly form? It's intuitive, we just take every single positive number and ignore all the negative ones. This gives us our starting peak, the number 1 largest sum. Now, how do we get the next largest sums? Any other subsequence is just a downgrade from our perfect max sum. If we leave out a positive number like 4, we lose 4. If we mistakenly include a negative number like negative 2, we lose 2. Every choice can be reframed as paying a non-negative penalty. This means we can completely eliminate negative numbers. Dropping a positive element or including a negative element costs us exactly its absolute value. We get a uniform array of penalties. We sort this array in ascending order because to build the smallest possible total penalties, we must start with the absolute smallest choices available. To kickstart this generation engine, we push a baseline state into our system, a penalty of 0 at an index of -1. From this spark, our engine moves forward to the very first penalty available, a at index 0, which is 2. This creates our first real state, a total penalty of 2 at index 0. From here, we branch out using 2 strategic choices. We can include the next element, expanding our subset by adding the next penalty value. Or, we can replace our current choice, which means we undo our last addition and swap it for the next element instead. This concrete logic ensures we systematically discover every possible penalty combination. We store every candidate state in a min heap and always process the smallest penalty next. Now the full intuition comes together perfectly. We pull the smallest element from our heap exactly k times. Because each penalty we extract is guaranteed to be greater than or equal to the last, subtracting them from our maximum sum of 6 yields our final answers in perfect descending order. On our fifth and final pop, the master formula delivers our exact answer, 2. We begin by calculating our absolute maximum possible sum. We loop through the array, adding all positive values to our running baseline. If we encounter a negative number, we transform it into its absolute value, turning our array into a uniform list of penalties. Next, we sort our uniform penalty array in ascending order. This guarantees that our state machine will process the lowest possible penalties first, minimizing the work our heap has to do. Now we set up our min heap, sorting items strictly by their penalty value. We initialize the heap by pushing our starting anchor, a total penalty of 0 at index -1. We kick off our extraction loop, which will run exactly k times. In our very first iteration, we pop the root of our heap. The current penalty is 0, and our index pointer is -1. We then decrement our counter. From this state, we check if there is a next index to look at. Since index 0 exists, we generate our include next state. We take our penalty of 0, add nums at index 0, and push the new state, a penalty of 2 at index 0, into our heap. Because our index was -1, we bypassed the replacement step. The loop powers forward. In each cycle, we pull the smallest penalty from the top of our tree, update our current penalty tracker, and push its unique include and replace child states back into the heap. The tree constantly auto-balances, keeping the next smallest penalty perfectly staged at the root. On our fifth and final iteration, the loop counter drops to 0 and the cycle terminates. The current penalty variable is holding a value of 4, which is the exact fifth smallest penalty possible. We subtract this from our absolute maximum sum of 6, delivering our final correct answer of 2. Let n be the array length and k the rank we need. Time is O of n log n plus k log k. We sort the absolute penalties, then perform k-min heap extractions, each pushing at most 2 new states. Space is O of n plus k for the sorted array and the heap frontier. Function ksum takes integer array nums and positive integer k. Initialize max sum to 0. Set n to the length of nums. For each index I from 0 to n-1. If nums at I is positive, add nums at I to max sum. Otherwise, replace nums at I with its absolute value. Sort nums in ascending order so penalties are non-decreasing. Create an empty min heap named costs. Push the seed state, penalty 0 at index -1. While k is greater than 0. Pop the smallest penalty index pair from costs. If a next index exists, compute the include penalty, current penalty plus nums at idx plus 1. Push that include state with index idx plus 1. If idx is not -1, compute the replace penalty, subtract nums at idx, add nums at idx plus 1. Push that replace state with the same new index. Decrement k by 1. Return max sum minus current penalty.